Okay, so good morning to all of you. Today I am going to teach you about some basic concept of molecular spectroscopy. The first thing which we taught in molecular spectroscopy is the Born-Oppenheimer Approximation. So my name is Dr. Prashant Kumar Srivastava. I am working as an assistant professor in Allahabad Degree College, and today we are going to learn about the Born-Oppenheimer Approximation. So the first thing which we have to understand is what are the differences between the atomic and molecular spectroscopy. So as we know, in the case of atoms, the angular momentum is conserved, and so we can classify the molecular atomic energy state according to the electronic angular momentum. However, in the case of molecules, this is not the case, and the angular momentum is not conserved in molecules. So let us suppose that we take a simple example of diatomic molecule. The total charge distribution in diatomic molecule is symmetrical about the internucleus axis. So the component of angular momentum along this axis is actually conserved, and we have to classify our molecular energy states according to this component. Second crucial difference between atomic and molecular spectroscopy is that in the case of molecules, we cannot ignore the nuclear motion as we can do in the case of atoms. So we actually take that nuclei is static in the case of atomic spectroscopy. However, in case of molecular spectroscopy, the nuclei actually vibrate along the internuclear axis, and this causes the vibrational motion, or we can say vibrational levels in the molecular spectroscopy. The second thing is that this molecule, the whole system of molecules rotates about its center of mass axis, and therefore there is a rotational degrees of freedom for this molecule, and according to this we have to classify the rotational energy levels. Now the Hamiltonian is very peculiar in the case of molecules. This is the molecular Hamiltonian, which you can see. That is, Hamiltonian consists of five parts. First part is the kinetic energy of electrons, all the electrons which are moving in the atoms. Second is the kinetic energy of nuclei. Third is the Coulomb interaction between electron. Fourth is Coulomb interaction between neutron, and fifth is the Coulomb interaction between electron and neutron. So the exact solution of this Schrodinger equation with the above Hamiltonian is not possible, and that's why we need the approximation to separate the variables. This approximation is actually provided by Born and Oppenheimer. These are the two scientists, Max Born and Robert Oppenheimer. So they actually proposes that in molecules, nuclei actually moves much more slower than the electron because of the large masses of the nuclei. So they approximate that the motion of electron at any instant is same as if the nuclei are fixed in the space. So means when there is an electronic motion, let us suppose that electron is moving from lower energy state to higher energy state, or higher energy state to lower energy state. At that instant, the nuclei remain fixed in space because nuclei is moving very slowly. The quantum mechanical equivalent of this above approximation or Born-Oppenheimer approximation is that we take the wave equation for electronic motion alone and solve, in which the nuclear coordinates appear simply as a parameter. Means nuclei is fixed. So we can treat the nuclei coordinates as parameters. They are not a variable. They are not changing with the time. So first thing we do that, and then the wave equation of motion of nuclei alone is solved, in which characteristic eigenvalues of electronic equation occurs part of potential energy function of the nuclear motion. So these are the two steps in which we apply a Born-Oppenheimer approximation to get the solution of this Schrodinger equation with this molecular Hamiltonian. So that's all from my side. Thank you very much.